Next thing in thermodynamics is molar specific heat capacity. Molar specific heat capacity. What is molar specific heat capacity? Write down a statement first. Amount of heat required to raise the temperature of unit moles by unit degree Celsius is called molar specific heat capacity. It's called molar specific heat capacity, and it is represented by C. So, what is molar specific heat capacity? You've got 1 mole of gas and you want to raise its temperature by 1 degree Celsius or 1 Kelvin. Degree Celsius or Kelvin. If I say you want to raise it by 1, then degree Celsius and Kelvin, they both are same because we are talking about difference. Difference wise, Celsius and Kelvin, they are always same. So, for 1 mole, if you want to increase its temperature by 1 degree Celsius, the amount of heat you supply, that is called C, molar specific heat capacity. Suppose we have n moles of a gas, and for n moles of gas, to raise the temperature by dT, heat supplied is dQ. For n moles, temperature is raised by dT, and in the process you supplied dQ heat. And if I ask you for 1 mole, how much heat will you supply? For 1 mole, you will be supplying dQ divided by n. For n moles, heat supplied is dQ. For 1 mole, it will be dQ by n. Similarly, for dt, heat supplied is dQ. For 1 Kelvin or 1 degree Celsius change, heat supplied will be dQ upon n dt. So, what is this whole thing? This is amount of heat required to raise the temperature of 1 mole by 1 degree Celsius. And therefore, this for us is what? C. That's the formula for C. Remember it like this, dQ upon n dt. In physics, we have a tendency to develop things for unit numbers. What is density? Mass of unit volume. What is velocity? Displacement covered in unit seconds. Gravitational intensity is gravitational force on unit mass. Similarly, for unit moles, unit degree Celsius change, heat supplied is dQ upon n dt, which is called what? C. Now let's understand this part with the help of different types of process. Let's first take the easiest value of C. If I ask you what is C for an adiabatic process, C for an adiabatic process. Think about it. What is an adiabatic process? In an adiabatic process, no heat transfer takes place with the surrounding. no heat transfer takes place with the surrounding. That means what is dq? 0. If dq is 0, then C is what? 0. For an adiabatic process, molar specific heat capacity is 0. Again, a one-liner statement type of thing. You can remember it in this form. What is C? Amount of heat required. What is an adiabatic process? No heat can be transferred. And therefore, C immediately becomes what? 0. Next, if I ask you what is C for an isothermal process? For an isothermal process, what do you think will be the value of C? What is C? Amount of heat required to raise the temperature by 1 degree Celsius. But in this case, you have a process which is what? Isothermal. For isothermal, what is dt? 0. Something upon 0 is what? Infinite. This C for an isothermal process is what? Infinite. And at times we say that this C is not defined. It's not defined. Both ways you should remember this thing. What is C for an isothermal process is what? Infinite if somebody uses this formula. But if you talk about isothermal, what is an isothermal process? A process in which you cannot change the temperature. And what is molar specific heat capacity? You need to raise temperature by 1 degree Celsius. On one hand you're saying that you cannot change the temperature, and on the other hand you're saying that you need to raise the temperature by 1. Both things cannot be true, and therefore we say that C for an isothermal process is not defined, but at times you will find that for mathematical formulation you can take C isothermal as what? Infinite. Now, if I ask you what is C for an isochoric process, then this for an isochoric process is something we are interested in. C for an isochoric process, it has a name, it's called CV. Molar specific heat capacity for an isochoric process is CV. Now, if this is CV for an isochoric process, then it's going to help us a lot. How will it help us? Look here. First of all, dq upon n dt. This dq upon n dt, it has become what? CV. CV for an isochoric. And therefore, what is dq coming? dq is coming n CV dt. That's your dq. N CV dt. But what was dq? dq was du plus dw. dq was du plus dw. What type of process we are interested in? Isochoric. For isochoric process, you know that work done is always what? 0. If it is 0, then look, we have got the value of du as ncv dt. This gives us du as ncv dt, or internal energy is coming ncvt. I had told you that internal energy of the system, it depends upon what? Temperature, and that formulation is present here. Internal energy is a function of what? Temperature, and is given by ncvt. Change in internal energy is du, which is ncv dt. We have developed this value of du or u with the help of an isochoric process. But remember, this du is valid for any type of process. With the help of isochoric, we could develop it easily. But we know that internal energy is a function of temperature. If you say it's a function of temperature, somebody told us that internal energy is 5T. This is the 5. Now, we had no idea what this 5 is, and therefore we took advantage of an isochoric process. The way you take advantage is in this part. dW becomes what? 0. And therefore, with the help of dq coming from this, you can directly get U as NCVT. Write down this statement. Although we have developed internal energy, although we have developed internal energy for an isochoric process, for an isochoric process, this formula is valid for any type of process. This formula is valid for any type of process. Wrote down this much, and then we'll see C for an isobaric process. Wrote down this much. Now look at molar specific heat capacity at constant pressure. dq upon n dt. This is C. For an isochoric process, we used CV. Volume is constant. For an isobaric process, we call it CP. Pressure is constant. That's your dq upon n dt, which is what CP. Now, what basically is happening when you write CP and CV? For an isobaric process, you're supplying some heat for n moles and you're raising the temperature by dt. And in the entire process, you're keeping pressure of the gas constant. Similarly, for an isochoric process, you're supplying dq heat for n moles, raising the temperature by dt, and in the process, the heat supplied, you found that, and you call it then CV. So, right now, this dq upon dt, dq upon n dt is what? Cp. If this is Cp, then first thing, we can write dq as, this dq is n Cp dt. But what is dq? First law says that dq is always du plus dw, which means this n Cp dt, n Cp dt is what? Du. What is du? I told you that for any type of process, du is n Cv dt. Although we are discussing isobaric process, but we know that du, its value is what? N Cv dt. This time round, it has nothing to do with constant volume. It's just that u, as a function of temperature, we have developed and we found that the coefficient in front of T is n into Cv. So, this is your du plus dw. What is dw? For an isobaric process, we calculated work in this form. P times V final minus V initial. Then we also found this work in terms of NR T final minus T initial. That was work for an isobaric process. And therefore, for an isobaric process, this dW can be written as nR dt. Small amount of work is what? Small amount of temperature change. What is T final minus T initial? Very small change, and you will call it what? dt. Look at this. N cancelled. Dt cancelled. This gives us Cp minus Cv, which is coming R. An important relation which is known as Mayer's formula. You can expect this question in your school examination. And remember the result, Cp minus Cv is what? R. Which also tells us that Cp is always greater than what? Cv. And that difference is what? R. And after some time, this equation will also help us in finding values of Cp and Cv for a given system. As of now, remember that Cp is always greater than Cv and the difference is equal to what? R. This is called Mayer's formula. Now let's understand why Cp is greater than Cv. Right here. Say we have two identical cylinders. They both have n moles of identical gases. Let's say in both you have got hydrogen. Now, for the first one, you have been told that you need to keep pressure constant. And for the second one, you have been told that you need to keep its volume constant. Initially, this is at temperature T and this one also is at temperature T. N moles, temperature T, N moles, temperature T. Everything is identical. Now, if I ask you that supply heat to this system, and when you supply heat, you must increase the temperature by dt. But you cannot change pressure of the system. For the second cylinder, again, you need to increase temperature by dt, but you cannot change the volume part. If for constant pressure you supply the heat, then part of that heat, you know that dq is du plus dw. Part of the heat supplied changes internal energy, and remaining part it does what? Work. In both cases, since you are raising temperature by dt, your du is what? Same for both isobaric and isochoric. This du part is what? Same. But in isobaric process, this piston is moving up because only pressure is constant, volume is not, and therefore this piston is going up. If piston goes up, that means this dw is also present. Whereas in isochoric, this piston is not moving. If piston is not moving, then for this work is what? Zero. If work is zero, that means for the isobaric part, your heat is increasing temperature or internal energy as well as doing some work. For isochoric, it is only increasing what? Temperature, that is internal energy, is doing no work, which means you can see that heat supplied for isochoric will be definitely less than the isobaric process. That's the reason behind Cv less than Cp. Note down this and remember this as derivation for Mayer's formula. Note down this. Let's see expression for adiabatic process. Although while dealing with work, I told you that for an adiabatic process, we use PV gamma as constant. Our aim is to establish this relation between pressure and volume for an adiabatic process. And with the help of this, we'll also understand how we can take advantage of first law, molar specific heat capacity, and all the things which we have learned so far. You can consider this as a numerical exercise where we are dealing with simply numbers like P and V. So let's start this for an adiabatic process. First law, dq is du plus dw. That's the first law. It's an adiabatic process, and therefore you immediately know dq is what? 0. What is du? For any type of process, du is always n cv dt. What is dw? You cannot use the work we have calculated for an adiabatic process, because in that I told you that we are already assuming as if we know this formula. But right now we have no knowledge of this formula, and therefore what is dw? For any type of process, dw is always what? P dv. Very basics. dq for an adiabatic is what? 0. du for any type of process is n cv dt. dw for any type of process is what? P dv. Our aim is to find relation between P and V. But you can see T is also present. Let's remove this T part. How do you remove this T part? We'll go for ideal gas equation. What is that? PV equals to nRT. Now this is PV equals to nRT. Let's differentiate this thing. Remember, nothing is constant. Pressure, volume, temperature, they all are changing. And therefore, how do you differentiate this thing? First function, differentiation of second, dV, plus second function, differentiation of first, dP, and these are constants. Differentiation of T is what? dt. If you find it difficult, then you can use x. First function, differentiation of v with respect to x, dv upon dx. Then v, differentiation of first function, dp upon dx. And r, differentiation of t with respect to x, dt upon dx. dx, dx, dx. It's present in denominator, all these three parts, and therefore is getting cancelled. Or you simply remember in this form, P dv, V dp, nr dt. So this is your relation between pressure, volume, temperature when they all are changing. Now let's put this in this equation. The equation we have got is P dv is minus of n cv dt, minus of n cv dt. But we have the value of n dt. What's the value of n dt? Put this value of n dt. This is cv, then n dt. N dt is coming P dv plus V dp divided by R. N dt is P dv plus V dv divided by R. This is P dv. This is also P dv. Take this P dv to this side and you get what? P dV common. Inside you've got 1 plus P dV. This negative sign, move it to the left, it becomes CV upon R. 1 plus CV divided by R. And on the right hand side, you're left with minus of CV divided by R, CV divided by R multiplied by V dP. Now, what is relation between Cp and Cv? You remember that Cp minus Cv is what? R. Look here. What is this? This is R plus Cv. What is R plus Cv? This is Cp, which is coming R plus Cv. And what is this? This is P dV R plus Cv whole divided by R. And therefore numerator becomes what? Cp. I hope you can see it. R plus Cv divided by R. This is Cp divided by R. On this side you've got minus of Cv divided by R into V into dP. Now R and R cancelled, and when you integrate you always take same type of variables on the same side. So this is P, this is dP, this is dV, this is V, and therefore what we'll take these variables to the same side, and therefore this part right here is first of all Cp divided by Cv, Cp divided by Cv multiplied by dV divided by V, and on the left hand side you've got dP divided by P. Simple thing, dV upon V, dP upon P, and shift the Cv to the denominator like this. Now once you form this, you have to integrate this whole part. When you integrate this thing, this is Cp upon Cv, Cp upon Cv, dV upon V. What is the integration of dV upon V? Log V. Log V. This side, minus of dP upon P. What is the integration of minus of dP upon P? Minus of log P plus constant of integration K. Since we are using C for molar specific heat capacity, I have taken K as what? Some constant. You can take it C, doesn't matter. Cp upon Cv log V minus log P plus K. Now what is this whole thing? First of all, you know the property of log. Property of log is one of the important property of log is log A to the power n. It becomes what? N times log A. And therefore, you can consider the Cp upon Cv as power, which is now, right now in the form of a coefficient, but you can always move this coefficient as power of V. You can always move this coefficient as power of A. And therefore, this left side is log V to the power of Cp upon Cv. Move this ln P to the left side. Ln P is what? Constant. Then next property of log which we will be using is this: log of A B is log of A plus log of B. Log of A B is log A plus log B. And therefore, this is log A plus log B, which becomes log of P V Cp upon Cv is what? K. Log A plus log B is log A into B. Now, what are you saying? Log of this part is a constant. Log of something is a constant number. That means this something should also be a constant number, which means PV to the power Cp upon Cv should be a constant. Now, this power Cp upon Cv, this Cp upon Cv, in short, is called what? Adiabatic gas constant gamma. Now, once you say it is gamma, you can see PV gamma is what? Constant. We have developed an expression for adiabatic process with the help of first law of thermodynamics. That's how you take advantage of these things. dq is 0. That means for some other process, suppose they gave you that dq for some other process is 5t, capital T. Write down that value of 5t. du is this. Write down dw in the elementary form, pdv, and then integrate the whole thing. If they say that heat supplied is directly proportional to pressure, write down that some constant into pressure. If they say that heat supplied is directly proportional to volume, some constant into volume. In this, heat is not being supplied, and therefore we are taking dq as what? 0. Once you take dq 0, look at these steps. You need to have little bit of knowledge of differentiation, log, and integration. Without maths, there is no physics. You know that. Note down everything before that. If you remember, while calculating work for an adiabatic process, I had told you that this gamma is greater than 1. Now, what is gamma? Cp upon Cv. And you know that Cp is greater than Cv. And that's the reason you say that this gamma is always greater than 1. Note down this derivation.